We come back now where we left off from the last video, looking at graphs of exponential functions. And as you can see, the equation I've given you here is a lot more complicated than the one we had before, which was f of x equals b to the x power, because now we have a constant that's times the exponential expression. We have a constant being subtracted from the x and a constant being added to this overall expression here. And each one of these things affects the graph. For example, if a is negative, it reflects the graph in the x-axis. And I'm going to use absolute value because I don't know if a is positive or negative. The absolute value of a is greater than 1. It stretches it vertically. Makes it seem like it's either going up or down a lot faster. If the absolute value of a is between 0 and 1, it shrinks it vertically, kind of crunches it in. Here, h is a translation. If h is positive, it shifts to the right that many units. If h is negative, it shifts to the left that many units. And here, this plus k, if k is positive, it shifts upward k units. If a is negative, it shifts downward k units. So I have a couple of examples here, and I seem like I have a tendency to forget to circle the ones from the review. But this first one here, there are two transformations from the graph that we just did in the last video. In the last video, we graphed y equals 2 to the x, which kind of did one of these things here. One minute. Excuse me. Now what we're going to do is we're going to have that same parent graph, but we're going to shift it to the left 2 units, and we're going to drop it down 1 unit. So if it helps you, create a t-chart of values, because you haven't done a lot of this. It's either that or graph them in stages. Now, normally I use -2, -1, 0, 1, and 2, but since I'm shifting it to the left, I'm going to use -4, -3, -2, -1, and 0, and I think that's going to give me enough points to get an idea of my sketch, because I can see that with this being a positive number, it's going to be exponential growth, it's going to be increasing. So hopefully I can help that with the pattern. -4 plus 2 is -2. 2 to the -2 is 1/4. 1/4 minus 1 is -3/4. -3 plugged in there. -3 plus 2 is -1. 2 to the -1 is a half. A half minus 1 is -1/2. -2 in there gives me 0. 2 to the 0 is 1. 1 minus 1 is 0 here. Plug -1 in. -1 plus 2 is 1. 2 to the first is 2 minus 1 is 1. And plug 0 in. 0 plus 2 is 2. 2 to the second is 4 minus 1 is 3. Now think about the original parent graph that I graphed in the last video, y equals 2 to the x. It went through 0, 1. It had the x-axis as a horizontal asymptote. And it had showed the increasing. In this case, you'll see some of those same exact attributes, except that everything's been shifted 2 to the left and down 1. So when I graph these points, remember what the original graph looked like. Here, let's just do the original graph again. I'll graph this quickly. It looks something about like this. This is y equals 2 to the x. Look what happens here. When I graph these points, -4, 1, 2, 3, 4, -3/4 is down here. -3, -1/2, -2, 0, -1, 1, and 0, 3, 1, 2, 3. You see I have the same 5 points? This thing has not been changed as far as stretching or shrinking. It's a rigid transformation of these two transformations, of these two translations. And my graph now, because it went down 1, the line y equals -1 is now its horizontal asymptote. And it does something like this. Oops, it goes down further and further like that. And the one in red there, that's our boy right here. Now this next one only has one transformation, and that's the graph of y equals 5 to the x with a -3 drop down 3 units. Everything else stays the same, so if it might help you, make a t-chart. -2, -1, 0, 1, and 2. Plug -2 in, 5 to the -2. is 1 over 5 squared, 1/25. So this is negative 2 and 24/25. So it's going to be practically negative 3. In fact, since it got shifted down 3 units, y equals negative 3 is going to be the horizontal asymptote. I'll go ahead and put that in right now. Plug negative 1 in. 5 to the negative 1 is 1/5 minus 3. It'd be negative 2 and 4/5. Plug 0 in. 5 to the 0 is 1. 1 minus 3 is negative 2. 5 to the first is 5 minus 2. Excuse me, minus 3 is 2. And 5 to the second, I don't think this one's going to fit. That's 25 minus 3, which is 22. Have to make it a lot taller. So I'm going to graph these points. Negative 2, and I'm going to approximate here with the fractions. Negative 2 and 24/25. So it's going to look practically smack dab on it. Negative 1, negative 2 and 4/5. Again, practically looks like it's on it. Maybe just a little bit higher, noticeable. 0, negative 2. 1, 2. And then this point is way up there to be at above the whiteboard. So it's going to go up very quickly. Now it's not going to be vertical, but it's going to practically be close to vertical. So I just try to draw it best I can. It is not turning into a vertical line. And that would be the graph of these two guys here, these two exponential functions that have some transformations. Now, besides pi being most people's favorite irrational number, e is probably the second most famous irrational number, named after the mathematician Euler, E-U-L-E-R, which is approximately 2.718281, and it goes on for forever and ever and ever. I think in the textbook it's got maybe an approximation with 20 or 30 decimal places. And we can find this value if we let x get really, really big and we evaluate this expression. 1 plus 1 over x, all that to the x power. Notice the exponent up there being a variable. If you put in bigger and bigger and bigger and bigger numbers in here, and evaluate it, you get a number that's closer and closer and closer to this. And eventually, we use the term limit. If the limit as x goes to infinity of this expression will be equal to e. When you have this positive number greater than 1, the exponential function that has that e as its base is called the natural exponential function, because there are a lot of things in nature that relate to the number e, both in terms of e being the base and something we'll talk a little about later, a logarithm having base e. So the natural exponential function f of x is equal to e to the x, you're going to have to get a calculator out, because with an irrational number like this, if I want to try to graph this, I have to plug negative 2, negative 1, 0, 1, and 2 in. I'm going to be getting some numbers that I can't do in my head. I mean, I can approximate it, but for example, this first number is approximately 0.135. Now, I don't know how many of you looked at that and said, oh, well, that's pretty obvious. This next one is 0.368, approximately 3 decimal places. Of course, it's a lot easier when you plug 0 in, because that's just 1. If you plug 1 in, e to the first is approximately 2.718, and e to the second, so a number a little bit less than 3 squared, should be a little bit less than 9. Turns out to be 7.389. Now, if I graph these 5 points, and I'll do the best I can by approximating, this would be way down here, practically on the line, a little bit higher up. 0, 1 is easy. 2.718, 1, 2, about there, and see, 3, 4, 5, 6, 7, this is 7 here, so it'd be up here just a little bit above, and we would get this graph. Again, it's an exponential function. It shows growth because the base is positive, greater than 1, and you can see it's increasing from left to right. All right, now, it looks a little bit like some of these guys here, different base, different growth rate. Now in this case, this guy here is based on this one here. Look at what we're doing. We're moving it to the right one, and then we are reflecting this in the x-axis. That's why when I drew my graph out, I don't have a lot of space up here. I have a space down here. So if I took this one right here, and this is the answer, by the way, to the graph to that, but if I took this one, and if I shifted everything to the right one, it would look something like this. Right? Where I would have the same y values here, but for different x's because I shifted it to the right 1 unit. That's what I'm trying to show you here with the -1. Well, if I take those values and I take the opposite of those values, here at -2, I will get approximately -0.5. I will get approximately -0.135, if I can sneak that in there. I will have approximately -0.368. Notice these two numbers here and these two numbers here. I will have at 1, I will have -1. At 2, I will have -2.718. And at 3, I will have -7.389. I hope you can see that. It looks like it's still on the screen. Now I'm going to graph those. -2, -0.5 approximately. Wait a minute, I have negative, oh, it would help if I put the decimal point in the right spot. The decimal point's right there. It doesn't increase and all of a sudden it decreases, -0.05, so that's practically right there on it. And then not much further down. And then still not much further down. -1, -1, 2.7, negative, and 3, 4, 5, 6, and this is -7 down here. So, be about here. And you can see how the graph has been reflected. At least I hope you can. Maybe this will help. So much easier to do this with graph paper. Oop. Especially if you don't have a real steady hand. And that's not going to be vertical. That's going to look like it's dropping down pretty quick, but it's not going to be a vertical line here. And you get the graph of this guy. All right, so this is the natural exponential function. Of course, that's the natural exponential function with a couple of transformations.